We are going to discuss how to change the order of integration in a multiple integral or iterated integral. Suppose we are given an iterated double integral, say integral from y1 to y2, integral from x1 to x2 of a function of x and y dx dy. So the order of integration is with respect to x first, followed by integration with respect to y. Suppose we want to change the order of integration, integrate with respect to y first, then with respect to x. There will be changes in the limits of integration, and that's what we are going to study or learn. How do we determine the new sets of limits of integration? Consider the following example. Reverse the order of integration of the following. Integral from 0 to 1, integral from 0 to 2y of 2x minus y dx dy. So the order is x first and then y. All right. We can do this if we know the region of integration, denoted by S usually. And so how is S determined? It is like this. First, observe that the form of this iterated integral is like this. No? The first set of limits, the innermost, are x values, x1 to x2, because the integration is with respect to x. And then the last set of limits, integration with respect to y, we have y1 and y2. So what you're going to do is this. For the first set of limits, equate x to each of these. So x equals 0 and x equals 2y. They are two equations. And in the for the last set of limits, since the integration is with respect to y, change this to equations y equals 0 and y equals 1. So here, first integration, lower limit is 0, so x equals 0. Upper limit is 2y, so x equals 2y. So what we are putting on the left is the variable of integration, x. And in the second integration, the variable of integration is y. So we set y equals 0. We get this, y equals 0. And then lastly, y equals 1. These are four equations. And equations have graphs. Just draw the graphs of those four equations. And whatever they enclose is the region of integration. So here, let me do first the x-axis and the y-axis are drawn there. Then our equations are number 1, x equals 0. That's a vertical line. There, the blue line, only a portion of the vertical line, x equals 0. This is the first integration, no, with respect to x. So second equation is x equals 2y, or normally we write it in the form y equals 1 half x. That is a straight line with the slope 1 half passing to the origin. That's the graph. A blue line passing to the origin is slope equal to 1 half. Third, y equals 0. That is a horizontal line. In fact, that is the x-axis. Y equals 0 there, x-axis. Then lastly, y equals 1. That is a horizontal line. There, y equals 1. So those equations have graphs enclosing a triangular region. Actually, equation 3, y equals 0 is redundant or is not needed. No? Even without that, you already have the triangle. So you may remove it. Now that we know the region, we can integrate in any order we like. We are already given the limits of integration when the order of integration is x first and then y next. So we reverse the order. Let's make it dy dx. By the way, that is the region S, colored yellow. The important points in the region are the intersections, the corners. We have 0, 0, we have 0, 1. These are obtained by solving simultaneously some of the equations among 1 to 4. Then this one is the intersection of the equation y equals 1, this line y equals 1, horizontal line, and the line y equals 1 half x. Solve them simultaneously, you get that point 2, 1. We can now integrate in the order dy dx, or with respect to y first and then with respect to x. With respect to y, so x equals constant, Refer to the figure. Look at the line segment which is part of the line x equals constant. So we draw a line x equals constant there. Segment of that line inside the region is colored red, and the endpoints will serve as our set of limits of integration with respect to y. So what is y below here and what is y there? Obviously the upper value of y is 1. How about here? It is not fixed. Y here is computed based on the equation of the line where that point is. This line is y equals 1 half x. Therefore, y here at the lower end point of the vertical line is 1 half x. Then what will you do? You will, okay, that's y1, let me indicate. y1 is 1 half x and y2 is there equal to 4. Then you will move that red line left and right until it covers the entire region S. The leftmost position is obviously here, where x is equal to 0, and the rightmost position is there, where x equals 2. So we have these limits. The innermost integral will have limits 1 half x to 1, and the outermost from 0 to 2. Okay. So I'll give you a few more minutes to look at the drawing and the result we obtained. As an exercise, this you will do later on paper, no? After the video lecture. To check whether we reverse the order of integration correctly, evaluate the original integral and also the result after reversing the order of integration, and show that for the original integration with respect to x and with respect to y, evaluate this iterated integral and show that it is equal to 2/3. After reversing the order of integration, we got different sets of limits. It is not a matter of interchanging these sets of limits only. No? Please take a look. Lower limit is 1 half x. There is no 1 half x in the original. 1 half x to 1, and then 0 to 2. Show that this is equal to 2/3. And as an additional exercise, evaluate the integral. This function is a little bit different. I made it 2y minus x. Evaluate this iterated integral. So integration is with respect to y first, then with respect to x. And then reverse the order of integration and evaluate again the resulting iterated integral. If you will do it correctly, the answer to both integrations is 0. So that is left to you as an exercise. That should be a simple exercise only. There is nothing difficult about this function to y minus x. It will be more difficult if the function will contain exponentials or logarithmic or trigonometric functions. But I avoided that because the important thing here is changing the order of integration. Okay, so thank you very much for watching. That is all for this lecture.